So good afternoon, everyone. So my name is Yidu. Currently, I'm a PhD student from Chair of Sustainable Construction, ETH Zurich. I'm very happy and honored to be invited for the talk today. Today I'm going to present some of work I did during my PhD studies. So the talk is a new low carbon impact polders with improved water resistance. So my talk will be divided into 5 different parts. So first, I will briefly introduce some background about Earth construction, and then I will introduce some recent development about polders, and then show the method or the way of our doing the polders, and then I will show some results from different aspects, and then finally will be the conclusion of my talk. As we all know, earth construction is not a new development in the construction sector. Earth materials have been used since a long time ago. So they are natural materials. We can find earth material. We can directly dig out from our ground, and they are simple and cheap. They don't need further processing. And with different size of the gravel, we can build a structure with different aim. For instance, for the wall protection, a very good example is the Great Wall of China. It's the running earth wall, and we also can build some structure for the human beings. Here we can find some housing in Yemen and some public space in Mali. Recently, because the global warming issue, we need to decarbonate our construction industry because all the benefit of the earth materials nowadays they are gaining renewed interest by the research and the builders. So here there are 2 recent earthen architecture fund which can found in Switzerland. First one is the ETH domain, and the second one is the herb processing center. Among the earth construction technique, polders is a very interesting technique to build with. As the name suggests, it can be poured like a concrete. So it's a liquid state of the earth materials. The benefit of doing this pouring is we can achieve dense packing with optimized water, but without additional energy input. And so they are quite easy to process, and compared to other earthen construction technique, is faster and cheaper, and most importantly, is more adaptable to modern construction industry. Of course, we have different way of doing the polders. My topic focuses on the deco process. So deco process is so we have some clay dispersant to deflocculate our clay at the beginning, and then following we have some additive which can remove the dispersing effect of the dispersant to make our paste rigid again. So then we have the time we can remove the framework at the beginning, and depending on the need, we can have a different reaction speed. For instance, we can have the slow reaction speed like a concrete. Also, we have very fast reaction like more like the shoot concrete. Yes, the deco process is quite cheap and easy to work with because we only need low dosage of dispersant and its coupled inhibitor. And compared with other system is more friendly. But if you think about the principle behind, all the additive put here, they don't change the nature of the clay materials. So that means the capillary force is still our main bonding force for the earth materials after drying, and still is quite sensitive to water, which is quite which is a big enemy of the earth materials. So then how can we improve the water resistance of the powders prepared with the same logic? Again, if we look back about the principle, so we have some dispersant attached to the clay H, and then provide some dispersion, and then following we have some additive which can remove this action by forming the new faces here. So in the end, we have the new faces and our matrix. If we want to increase the water resistance, we need to functioning these new faces to be more water resistant. Currently, we don't have this option because all the reported additive combination, they are all mineral-based. They don't have this function to provide the water protection to the matrix. So we need to think about, or we need to discover a new combination of the dispersant and the anti-dispersant agent. We got some inspiration from the vernacular construction practice. After a detailed literature review, we found the tannin. So tannin is a very interesting material. So they can be used as a coating to protect the earthen structure from water erosion. Here in Burkina Faso, the local people use the tannin extraction solution mixed with the coagulant and the local soil to produce the plaster to protect the wall from water erosion. Another interesting fact about tannin, they can use as a stabilizer for the earth materials, especially for the iron-rich soil. The third thing is tannin can be used as dispersant. So with all this information in mind, then we can we might get some clue, or we can think about how to design the powders with water resistance, or with improved water resistance. First, we need to prove tannin can be used as dispersant, because there is a huge variation in the tannin family. So they can be divided into three families. First one is hydrolysable tannin. This one can be further divided into coagulant and allergic tannin. And second family, we have the condensed tannin. We also have a complex tannin. At the beginning, we chose three types of tannin to test their dispersant efficient, and two types of coagulant tannin, three types of allergic tannin, and three types of condensed tannin. So in the end, we found allergic tannin, they are quite efficient compared to other extract. So in the end, we chose tannin extracted from the oak tree. Here I just name it OT, so it represents oak tannin. So after this test, we need to know why the tannin can be used as dispersant, or in another word, we need to understand how the tannin interact with our clay particle. So after we did, then we did some test of the XRD and the infrared. So we found after incorporating oak tannin in the kaolinite paste, all the intensity of these four hydrocell group bond, they are decreasing, but they are not decreasing proportionally. So the outer hydrocell group decreased more than the inner one. So it means with XRD spectra, we can safely conclude tannin tend to interact with the outer hydrocell of the kaolinite, which is mean tannin interact or absorbed on the edge of the kaolinite. Of course, with this information, we can think about some way to increase this dispersant efficiency. We can further adding sodium hydroxide, because the sodium hydroxide can deprotonate and disaggregate the tannin structure to make it more negatively charged, and we have more abundant negative structure afterward. So after knowing tannin can be used as dispersant, then we need to think about how can we remove this dispersant effect. Meantime, to maintain or even increase the water resistance. So if we look back about the vernacular practice, another important element is the iron-rich soil. But we don't have this soil around the world. So we simplify this practice into additive solution. So we chose iron chloride one. So here, as you can see from the picture here, after putting iron chloride in the tannin solution, we saw some precipitate form in the solution. So that means the tannin can be precipitate out of the solution by the iron chloride. And in the meantime, the paste, the yield stress of the paste is getting higher. And we can say more clearly with the oscillation swap curve. After putting oak tannin, so the paste is more liquid, so we have lower elastic modulus and higher critical strength. But once we put iron chloride one, so the elastic modulus is suddenly increased to a value close to our reference and even higher. And same for the critical strength is suddenly getting short. And the critical strength is even lower than our reference. So that means this deflocculation action brought by the tannin already been removed. So the paste is not liquid anymore, so they are now in the coagulated state. We also did some water resistant test of the sample. So on the left is a deep test. And so we can say after putting this additive solution, the sample getting more water resistant. Here we can say a delayed fracture time of the immersion part. And we also say the sample surface is more intact after 1 hour 1 hour immersion. So tannin combined with iron chloride can provide some protection, or can increase the sample resistance to the water disaggregation. We also did some tests about the water ingression. On the right, we test the ingression time of the droplet to the sample. So we can say after using this mixture, the sample or the water is getting more difficult to penetrate in the samples. So in short, we can conclude this oak tannin combined with iron chloride can protect the sample internally and externally. So the internal protection is to increase the sample resistance to water disaggregation, and the external protection is to slow down the water ingression. Then we need to think about how can we control this complexation reaction. Then we have we have more time to work with our materials at the beginning. The simple way to do it, we can choose iron component with different solubility. So in the lab, we chose 5 different iron components with different solubility. Same like before, first one is iron chloride, which is quite soluble, and iron citrate is slightly soluble, and also we have the phosphate is sparsely soluble. In comparison, we also chose iron hydroxide and iron oxide, which are insoluble. As you can see here, the picture showing here, right after the mixing, we accept the iron chloride, all the rest, we don't see any precipitate. The color, the solution remain yellowish, but with the time going, we saw some precipitate form in the chlorate, citrate one and the phosphate one, but not hydroxide and oxidized one. And the reaction speed is chlorate, for sure chlorate one is super fast, and following is the citrate one, and the slowest is the phosphate one. We also did some characterization of the precipitate formed in the solution. Here is the result after mixing 48 hours. So although we have different reaction speed, but the final precipitate of the citrate is quite close to the chlorate one. But for the phosphate one is a little bit different. We still have some undissolved or unreacted phosphate in the precipitate. So that means with 2 days are not enough for the phosphate one to fully precipitate the tannin out of the solution. We also did some rheologic experiment. We need to test this selected iron component can finally rigid or can finally coagulate our paste. Same like before, we also did some oscillation test. On the left is the paste right after mixing. The measurement did right after the mixing. So as we can see at the beginning, so even we put iron citrate in the mixture, the rheological behavior is quite similar like to the pure tannin. So it's quite liquid at the beginning, but with the time going, so we say the curve slowly moving toward to the reference one. So that means they are not liquid anymore. They are rigid, and this dispersing effect of the tannin has been removed by the citrate one. The interesting thing is the phosphate. Even after resting of 48 hours, so the paste is still liquid-like. Yes, we saw some precipitate form in the solution, but not fully. With this 2 days, they are not sufficient, or they are not strong enough. The affinity of the phosphate is not strong enough to remove all the dispersing effect of the tannin, even with the higher addition. And we also tested continuous sharing, so they didn't help to remove this dispersant effect of the tannin. So yes, we also test the chlorate with different tannin extract to make sure it's more robust. So here we choose the tannin extractor from the grape seed and oak trace, but without treatment, and the chestnut trace and the spruce trace. They are so citrate one, they all work well. So at the beginning it's quite liquid, but after 2 hours it's kind of rigid. It not flow anymore. And we also did some. We also measured the compressive strength of the sample after drying. Except we can adding phosphate one. Adding iron chlorate. We can not only can remove the dispersing effect, we can also further increase the strength. And the higher addition, the higher increasement. Okay, so now we have the platform to work with, and then we can place things around. So yes, we have tannin as a dispersant to make our paste more liquid, and then we have the iron chlorate to remove this dispersant effect slowly. So then we have some time to cast. And because all this reaction happened with the hydrocell group of the tannin, we still have some other active site in the tannin, for instance, this side or this side. So for sure, we can employ other modification of the tannin first to make it more, or to make it to increase the dispersing efficiency. In that case, we can further reduce the water addition, and of course, by this combining action, we can further increase the strength, and most importantly, we can just improve the water resistance of the sample here, like here. So yes, this is my conclusion. Yes, in short, it just tannin can be used as a dispersant, and further incorporating sodium oxide can increase the dispersing efficiency, and iron ions can remove this dispersant effect, and the complex can provide some water protection of the sample. And then we can control this complexation reaction by using less soluble iron component, and with this kind of platform, we can employ more or other modification to produce the powders with better water workability, higher strength, and improved water resistance. Thank you for your attention, and I hope I make it clear. If you have more questions, feel free to contact me. Thank you.